day and welcome to DepEd TV, a venue where we can be in one place virtually, even from different locations in reality. This is Teacher Rev, your grade 11 math teacher, your guide to an exciting and amazing math venture. Do you still remember taking an achievement test? Have you ever wondered what is it for? How about measuring your height and weight during the first week of your PE class to know your body mass index? Have you ever tried to determine the location or make inference about your grades, height, or weight in the distribution? This lesson will direct us to appreciate the answers to such queries we have. Today, be ready to be captivated by the exquisiteness of normality as we delve into our discussion of normal random variable and the standard normal variable. Let's start by looking at the given distribution. The distribution of the height in centimeters of the 16 teachers of SCNHS was presented below. Construct a histogram for the random variable. Can you still recall classification of random variables? Remember, it can be discrete or continuous. What kind of random variable is the height? If your answer is continuous, your answer is correct because it can be measured. This time, let us look for the mean. What is the mean of the distribution? By analyzing the illustration, the mean of the distribution can be found at the center, which is 141 centimeters. What have you noticed on the two sides of the distribution? The distribution from the center to the right is a mirror of the distribution to the left as shown. Normal probability distribution is a probability distribution of continuous random variables. It shows a graphical representations of random variables obtained through measurement like the height and the weight of the students. The percentile rank of achievement tests or any data with infinite values. It is used to describe the characteristics of populations and help us visualize the inferences we make about the population. It also used to determine the probabilities and percentile of the continuous random variables in the distribution. The graphical representation of the normal probability distribution is popularly known as the normal curve. Let's go back to the histogram. Since this represents the height, then it is an example of a graphical representation of the normal distribution or a normal curve. A normal curve has its own properties. Let's discuss its properties by answering several questions. What have you noticed on the shape of the normal curve? If your observation is that the normal curve is bell-shaped, then that is a good observation. One of the properties of a normal curve is that it is bell-shaped. What does the center do with the normal curve? If your answer is that it makes the normal curve symmetrical by the center line, then you're correct. Another property of normal curve is that the curve is symmetrical about its center. This means that if we draw a segment from the peak of the curve down to the horizontal axis, the segment divides the normal curve into two equal parts or areas. Let's go back again to the histogram. Earlier, we observed that the mean is 141. What about if we arrange all the values in increasing order? What value will be in the middle? That is good when you answered 141. So the median is 141. What value appears most in the distribution? The value with the highest frequency is 141, which is the mode of the distribution. What have you noticed on the values of the mean, median, and mode? Exactly. If your observation is that they have the same value, you are correct. The third property of a normal curve is that the mean, median, and mode coincide at the center. This also means that in a normal distribution or a distribution described by a normal curve, the mean, median, and mode are equal. What symbol do you see in the label below the normal curve? If your answer is standard deviation, that's the correct answer. The fourth property of normal curve is that the width of the curve is determined by the standard deviation of the distribution. What have you noticed towards the opposite end of the distribution? The tails of the curve are plotted in both directions and flatten out indefinitely along the horizontal axis. The tails are asymptotic to the baseline. A portion of the graph that is asymptotic to a reference axis or another graph is called an asymptote, always approaching another but never touching it. The last property is that the total area under a normal curve is 1. This means that the normal curve represents the probability or the proportion or the percentage associated with specific sets of measurement values. A normally distributed random variable with a mean of 0 and standard deviation of 1 is called a standard normal variable. It is presented using standard normal distribution where the center of the curve is 0, which is the mean, and added 1 unit from the center to the right and subtracted 1 unit from the center to the left. The shape of a normal curve is based on the two given parameters, the mean and the standard deviation of the distribution. When comparing two distributions, each described by the normal curve, the following are the three situations based on the said parameters. First, when the means are not equal but the standard deviations are equal. What have you observed of the normal curve? Exactly, the curves have a similar shape but centered at different points. Second, when the means are equal but the standard deviations are not equal. What have you observed of the normal curve? If your observation is that the curves are centered at the same point, but they have different height and spreads, then your observation is correct. When the means are different and the standard deviations are also different, what have you observed of the normal curve? The curves are centered at different points and vary in shapes. If that is your answer, then you got it right. We can easily understand the functions of normal probability distribution in real-life situations using the empirical rule. The empirical rule is better known as 68, 95, 99.70% rule. This rule states that the data in the distribution lies within 1, 2, and 3 of the standard deviation from the mean are approximately 68%, 95%, and 99.70% respectively. The area of a normal curve is equal to 1 or 100% as stated on its characteristics. There are only few data which falls 0.30% outside the 3 standard deviation from the mean, which indicates 0.15% towards both ends. Let's have an example. For instance, the distribution of the grades of the senior high school students in statistics and probability for the third quarter is shown in the figure. Using the empirical rule, we can say that the distribution of the grades of the senior high school in statistics and probability are distributed normally because the shapes of the graph is bell-shaped and symmetric about its mean, which is 87. This also indicates that most of the students' grades fall close to the mean and fewer of them are far below or above the mean. We can say that 68% of data lies within 1 standard deviation from the mean have a grade of 83 to 91. 95% of data lies within 2 standard deviations from the mean have a grade of 79 to 95. 99.70% of data lies within 3 standard deviations from the mean have a grade of 75 to 99. Let's have another example. The scores of the senior high school students in their statistics and probability quarterly examination are normally distributed with a mean of 35 and a standard deviation of 5. From the given problem, we know that we have a normal distribution, which means we have a normal curve, with a mean of 35 and a standard deviation of 5. If we want to know what percent of the scores are between 30 to 40, what should we do? The first thing that we have to do is to draw a standard normal curve and plot the mean at the center, which in this case is 35. Let us consider one standard unit away from the mean, meaning one standard unit before and after the mean. Remember, a normal curve is symmetrical. That is, 35 minus 5 is 30, and 35 plus 5 is 40. This time, let us consider two standard units away from the mean, which is 35 minus 2 times 5 is 25, and 35 plus 2 times 5 is 45. This time, let us consider 3 standard units away from the mean. That is, 35 minus 3 times 5 equals 20, and 35 plus 3 times 5 equals 50. Note that the scores of 30 to 40 falls within the first standard deviation from the mean. Therefore, the scores that fall between 30 and 40 is approximately 68% of the distribution. How about if we want to know what scores fall within 95% of the distribution? What should we do? Since 95% of the distribution lies within 2 standard deviations from the mean, then the score corresponds to this area of the distribution or scores from 25 up to 45. Let us remember that one of the properties of a normal curve is that the total area under the curve is equal to 1, since the standard normal distribution is defined as normally distributed random variable having a mean of 0 and standard deviation of 1. The 50% of the region under the curve is below the mean and the other 50% is above the mean. We can easily identify the area of the regions under the normal curve by using the table of areas under the normal curve, which is also known as z-table. The value from this table will describe the area of the specific region of the curve to the left of the given z-value. But have you wondered how are we going to use the table of areas to find the area under the normal curve? Let's have an example. For instance, we want to find the area to the left of negative 1.69. First, split the given z-value into 2 parts. One part is the ones and tenths together and another the hundredths. Then, the intersection of these numbers will be the area of the normal curve to the left of the z-value. The area to the left of z equals negative 1.69 is 0.0455. Note that the area under the normal curve will always be less than 1 since the total area under the normal curve is 1. Now let's consider a more organized way of finding the area. To be able to find the area of the corresponding z-value, we need to consider several steps. First, draw or sketch a normal curve and locate the given z-value on the normal curve. Once you have located, put a boundary line. Second, shade a region of the curve according to the condition of z-value, whether it is below, above, or between. Below meaning the left side of z-value is shaded. Above meaning the right side of z-value is shaded. And between meaning the shaded area is between the two values. The third is, use the table of the area under the normal curve to find the corresponding area. First, split the given z-value into two parts. One part is the ones and tenths together, and another the hundredths. Note that the intersection of these two numbers is the value that represents the area under the normal curve to the left side of the z-value. So the default is that the shaded area is at the left of the z-value. The fourth is, choose the appropriate operation based on step 2 and 3. Three conditions may happen. First, when the z-value is to the left or any related terms, just write the value we obtained in step 3. If the shaded area is at the left or below the z-value, since the table provides the area of the normal curve to the left of the z-value, then the intersection is the area of the shaded region. Note that the area indicated in the table is the area at the left side of the z-value. We know that the area under the normal curve is 1, thus to get the area on the right side, we need to remove the area in the left side, so the remaining represents the shaded area on the right side. Thus, when the z-value is to the right or any related terms, subtract 1 by the obtained value in step 3. Note that the area indicated in the table is the area at the left of the z-value. Then we can remove the area of the smaller from the area of the bigger. When the shaded region is in between of the two z-values, subtract the biggest by the smallest value obtained in step 3. The last step is to label the shaded region and draw a conclusion. Let's have an example as we go through the steps. For example, we want to find the area that corresponds below z equals negative 1.35. First step is to draw a normal curve and locate the given z-value on the normal curve. We need to locate the z-value on the horizontal axis and draw a boundary line. Second step is to shade the region of the curve according to the condition of z-value, whether it is below, above, or between. In this case, we shade below negative 1.35, meaning to the left of negative 1.35. Third step is to use the table of the area under the normal curve to find the corresponding area. In this case, we need to split the given z-value into two parts. One part is the ones and tenths together, and another the hundredths. Then the intersection of these numbers will be the area of the normal curve to the left of the z-value. The intersection is between negative 1.3 and 0.05, which is 0.0885. The next step is to choose the appropriate operation based on step 2 and 3. Based on the sketch, when the z-value is to the left or any related terms, just write the value we obtained in step 3, since the shaded region on the curve is to the left of the z equals negative 1.35, and the intersection between negative 1.3 and 0.05 is 0.0885. Therefore, the area of the shaded region is 0.0885. The last step is to label the shaded region and draw a conclusion. Therefore, the area that corresponds below z equals negative 1.35 is 0.0885. Let's have another example. This time, let's find the area between z equals negative 1.30 and z equals 2. First step is to draw a normal curve and locate the given z-value on the normal curve. So, the boundary will be drawn at z equals negative 1.30 and z equals 2. Second step is to shade the region of the curve according to the condition of z-value, whether it is below, above, or between. In this case, we shade between z equals negative 1.30 and z equals 2. Third step is to use the table of the area under the normal curve to find the corresponding area. We need to find two intersections for the smaller z-value and the bigger z-value. The value that corresponds to z equals negative 1.3 is 0.0968, and z equals 2 is 0.97725. The fourth step is to choose the appropriate operation based on step 2 and 3. When the shaded region is in between of the 2z value, subtract the biggest by the smallest value obtained in step 3. Since the shaded region is within the 2z values, subtract 0.0968 from 0.97725. The difference is 0.8804. Therefore, the area of the shaded region is 0.8804. The last step is to label the shaded region and draw a conclusion. Therefore, the area between z equals negative 1.30 and z equals 2 is 0.8804. In solving real-life problems involving the normal curve, it is particularly important to convert a random variable to standard normal variable or z-score. This procedure is known as standardizing or standardization of random variable, where a standardized value is called a z-score. A z-score is a measure of the number of standard deviation a particular data value is away from the mean. Suppose your score of the test in probability and statistics is 39, and the scores are normally distributed with a mean of 33 and standard deviation of 3. Let's start by constructing the normal curve first. Since the mean is 33, that means one standard deviation away from the mean would be 33 plus 3 equals 36, and 33 minus 3 equals 30. Same way, the values 2 standard deviation away from the mean are 33 plus 2 times 3 equals 39, and 33 minus 2 times 3 equals 27. Lastly, the values 3 standard deviation away from the mean are 33 plus 3 times 3 equals 42, and 33 minus 3 times 3 equals 24. Now, let's go back to the problem. If you scored 39, describe your score from the mean using its standard deviation. If your answer is that your score is exactly 2 standard deviations above the mean, then your answer is correct. How about if you scored 30? How will you describe your score from the mean using its standard deviation? If your answer is 1 standard deviation below the mean, then your answer is correct. From a normal curve, all values that are above the mean have positive z-scores, and all values that are below the mean have negative z-scores. What about if you obtain a z-score of negative 3? This means that your score is 3 standard deviations below the mean. That is, 33 minus 3 times 3 equals 33 minus 9, which will have a result of 24. Given any value x from a normal distribution with mean and standard deviation, to convert x to a z-score, you need to, first, subtract the mean from x. Then, divide this quantity by the standard deviation. The formula used in converting a random variable x to a standard normal variable z is shown. Let's have an example. Suppose IQ scores are normally distributed with a mean of 100 and standard deviation of 10. If your IQ is 85, what is your z-score? The first thing is to identify what we have and what we are looking for. Since we're looking for the z-score, we can use the formula in finding the z-score. Since this score is below the mean, we expect that the z-value will be negative. But with regard to the exact value, let's look at the computation. Using the formula, let's substitute the values. Performing the operation in the numerator, we have negative 15, with the denominator is 10, then the z-value is negative 1.50. If you obtain the score of 85, this means that the z-score is negative 1.50. Let's have another example. The heights of teachers in Santa Catalina National High School are normally distributed with a mean of 150 centimeters and standard deviation of 15 centimeters. The height of Sir Victor has a z-score of 3.25. What is the actual height of Sir Victor? In this example, the z-score is given while the normal random variable is unknown. So let us derive the formula for the z-score. Let's multiply both sides by the standard deviation, add the mean on both sides, then we can solve for the score using this formula. To solve for the score, let's recall what we have and use the new formula. Note that the z-score is 3.25, which is positive, meaning the score is above the mean. So let's substitute the values and solve. The product of the z-score and the standard deviation is 48.75. Increasing the product by the mean will give us 198.75. Thus, the actual height of Sir Victor is 198.75 centimeters. Today had been a great learning experience. So, see you next week on another Math Venture with Teacher Reb. Remember, don't stop until you're proud. Learning math takes time. Bye!